All right, so our speaker today is joining us remotely from Google DeepMind, where he heads two AI-related research teams, and he'll be telling us about challenges and opportunities in robust and reliable AI. As you can see, he's joining us remotely, so there are going to be a couple of points of order here about asking questions. At the end, please come up to the podium and ask the question of the computer here so that our remote guest can hear and respond to you. All right, actually, all right, I'll start over, assuming that that was not projected. So we're pleased to welcome our guest, Pushmeet Kohli, from Google DeepMind, where he directs two AI groups. He'll be attending remotely, as you can see. So please, at the end of the talk, come up to the podium to ask your question of his telepresence embodiment up here.
Hello? Okay, so can everyone at the back hear me by wave of hands? Oh, good. Okay, so first of all, it's a pleasure to talk at this event. I'm really disappointed that I couldn't attend in person, but in some sense, basically, it's for the better. Sort of carbon credits got saved and so on. So the title of my talk is going to be towards robust and explainable artificial intelligence, and I'll sort of go into a bit of detail as to what I mean by being robust and explainable. So at the end of the day, we are interested in machine learning. But why are we interested in machine learning? We are interested in machine learning to solve problems. So one key question when you try to use machine learning and artificial intelligence to solve problems is to sort of understand, when have you solved the problem? How do you quantify success? What does solving a problem really mean? So here's the example. This is the problem of image classification on ImageNet, on the ImageNet benchmark. So here are 15 images taken from a very popular benchmark called ImageNet. Many of you would have heard about this. It sort of was one of the drivers for the recent excitement of research in deep learning. And these 15 images show you different images of birds, different species of cats, different species of dogs. Now, how many of you can confidently, accurately claim to recognize each species that is being depicted in these 15 images? Anyone? Maybe one person, maybe not, not very confident. So, a state-of-the-art deep learning-based system can recognize accurately all these species. And not only this, it is able to recognize 1,000 different categories, much better than any human would be able to sort of detect. Now you would say, well, that's superhuman. Like, this system is definitely behaving in a superhuman sort of way in terms of its perception abilities. Now, the exact same system which we just declared superhuman in its ability to detect and recognize these images, when given these two images, says one is a school bus and the other is an ostrich. The very same system. Now, what is really happening? What is really happening is that when we test humans, when we test the intelligence of humans, we can make certain assumptions that if a human is able to answer certain questions, then they can generalize to these other questions. And those assumptions that we make about evaluation and performance of human intelligence fail when we try to evaluate machine-learned neural networks, because they exhibit a different kind of intelligence. And generalization in neural networks is of a different form. So what happens here? The basic sort of thing that this network is not being able to enforce is this issue of insensitivity to small magnitude noise. So here I am sort of saying there's a very simple sort of specification which says that for all inputs in the training set, if there is any sort of x which is close to the input under some LP norm, then that should mean that the label that the classifier f of theta assigns to this particular input should be the same as the label it should assign to the original sort of image. So this is a very simple specification, and somehow this superhuman classifier, which was able to detect all these different species, is not able to conform to this specification. Now, this has been very well documented. There's a lot of research now going on adversarial examples and how can we get rid of them and so on and so forth. But this is not just an issue of image classification, right? When we think about using benchmarks to evaluate whether a system shows certain competencies, we should be very careful. Solving image classification, solving the problem of image classification requires you to solve the problem of ImageNet or MNIST. But solving ImageNet or MNIST does not mean that you have solved image classification. And I think this is something that the machine learning community and the artificial intelligence community needs to understand, that benchmarks are important, and benchmarks, sort of getting good results on benchmarks are important, but we shouldn't declare success just on the basis of good performance on a specific benchmark. And this is what the phenomena of adversarial examples is sort of showing us. This is not just true for image classification, it is true for other domains as well. So here's another very popular domain, this time of machine translation, where neural networks and deep learning, neural networks being able to translate sentences from one language to another at a very, very high accuracy, previously unseen accuracy. So here's a neural network, a sequence-to-sequence model, which can take a variable length sentence and can output of English. And it performs really, really well. Like this blue score is basically it tells you, but the blue score of 27.6 shows you that it's a very good translation system. Now the same system, if you give it a normal sort of input, it will give you a correct result. Now the same system, if you give it some other sort of nonsensical input, like a human translator, which would take that nonsensical sort of input and say, well, I don't know what you mean. What this system does, it goes into a crazy loop. And it goes into this non-terminating state where it basically, it creates a buffer overflow. It produces an extremely long output, which the downstream sort of systems were not ready to sort of take on. So this just shows that machine learning models are consistent with the input-output examples that were presented to them in the training data, but other specifications that we expect them to conform to, they do not naturally sort of are consistent with those specifications. Here's another example. So you have a self-driving sort of policy on the simulated driving game called, simulated environment called Torps, and it performs really, really well, but then out of the blue, after like 3,000 different tracks, it suddenly crashes in a very, very bad way. Similarly, here is a policy which was controlling a humanoid robot, and it would perform flawlessly, and you would sort of declare it correct, but after 300,000 states, somehow it just completely fails. So how can we basically reason about the deployment of these systems in safety critical applications where these rare failures can incur a very, very high loss? So the title of my talk was towards robust artificial intelligence and explainable artificial intelligence, but another title could have been towards rigorous testing of machine learning systems. How should we go about really understanding what are the failure modes, what are the competencies of machine learning systems as we start deploying them in the real world? So what do I mean by rigorous testing of machine learning systems? Of course, we evaluate the performance of machine learning systems on benchmarks. We see what is the accuracy on the test set. But there are other sort of ways that we could test machine learning systems in terms of normally inspired from the work that has happened in the software verification sort of community. We can sort of reason about whether machine learning models are compliant with various properties or specifications, such as robustness to adversarial transformations, or do they generalize well to variations present in the real world or encountered in the real world? Are they fair? Are they compliant with regulations regarding what kind of data can be used, what kind of dimensions or information can be used in particular cases? Now, there are two key issues with doing this for machine learning systems. One is to formalize what are the important specifications that we want to be consistent with. And then secondly, how do we change the whole machine learning paradigm so that it can become consistent with these specifications? And those are the key sort of challenges for enabling this kind of rigorous testing of machine learning systems. Now, of course, the formalization of specification is something that, as machine learning scientists, we cannot do. This is something that has to be done in a multidisciplinary fashion with social scientists, with people who really sort of care about how machine learning systems are supposed to behave. And then, while the machine learning community can work on how do we ensure that, suppose society has specified this is the behavior we expect, how should we make sure that machine learning systems can be trained to conform to those specifications? So I'll divide the spec-consistent AI theme of research into three different parts. One is rigorous testing of AI systems. Secondly, developing robust AI systems. And finally, verifying AI systems. So in rigorous testing, you are essentially trying to rigorously check conformance to different specifications of interest. In developing robust AI, you are trying to train machine learning models so that they are consistent with certain specifications. And in verifying AI, you are trying to formally guarantee that certain machine learning systems can be proved to be consistent with certain specifications. So, as a case study, I will sort of take this example of a very simple specification, which is invariance to perturbations. So, the specification is very simple. It essentially says that for all x in the training set, if there is any sort of x which is close to these images under some LP norm, then that should mean that the classifier should assign the same label as it sort of gave to the original sort of image. Is this specification clear to everyone? Yes? Like how many, is this, by show of hands, is this understandable? Okay, sounds good. So now here's a simple specification, and I will sort of use it on a very simple sort of image classification problem. So you are given these images from the MNIST dataset of numbers, and there's a neural network which takes as input this image, and it's supposed to classify and is supposed to predict the label assigned to this image. In this case, the value weight. So the problem is that there are some things called adversarial perturbations where you somehow very mildly change the original image, and if you give this new image of 8, it will be classified. These are not made up, these are real images. And it is quite remarkable that these systems fail so easily. Now, of course, the machine learning community, this is a crisis, right? For the machine learning community, we have to fix this. So there has been a lot of research happening in the machine learning community on how do we rigorously test and train machine learning systems which are robust to these kind of attacks. And so there was a competition which was organized in NeurIPS 2017. This is basically the top tier machine learning conference equivalent to PurPL and PLDI. And there were a number of different papers which have been sort of proposed for this approach. Many of them have won awards and so on. And so this competition was trying to sort of evaluate the effectiveness of these methods. So here were the results. And you see that these sort of 5 different categories, they would sort of report, this is their accuracy on the data set. And this under attack. So this is basically, these sort of models would generally have very, very high accuracy, right? Almost in the 90% sort of range of predictive accuracy. But under attack, when an adversary is systematically trying to find images of the types that I showed you, which adversarially sort of created, then the performance of these systems sort of drops, right? It drops to around as sort of shown, in some cases 20, in some cases 74, from very high 90s. Now, in order to see what was really happening, we decided to re-implement all of these methods in our in our lab, and we looked at what was the performance. And as you can expect, I mean, these are our implementations, but these were roughly sort of similar, right? The numbers were different, but the trends did not change that much. But what happens now if you slightly increase the strength of the attack? So all these numbers were using a specific mechanism to find the adversarial image. If we now slightly make that mechanism stronger, you get these kinds of results. Complete dramatic reversal in terms of the accuracy. So these models are not able to, they're always attackable. The adversary always succeeds in some sense. So this just shows how problematic this situation is. So let me tell you why this is so difficult. I mean, I don't expect you to sort of know about completely neural networks, but just let me sort of give you some sort of an illustrative toy example of how a neural network sort of works. You are given some high-dimensional sort of input at one end. There are a series of operators that are applied to that input, and then at the end, you basically are able to get a prediction. So traditionally, when you train a neural network, what happens is you take your input X, you will sort of propagate it down through your network, you look at what is the prediction that is being made, you compute a loss, and then you try to do gradient descent on the loss. backpropagation. You are trying to sort of adjust the parameters of the neural network such that basically the network exhibits slow loss. So now what I'm going to do, I'm not going to sort of operate with point sort of samples. I'm going to operate much like we do in abstract interpretation. I'm going to basically look at the whole, I'm going to sort of now work with whole spaces. So the specification that I had sort of talked about, which was that if, so around a sort of input point, I want consistency in labeling. So this pink box is showing or expressing that specification in some sense. It's saying there's a hypercube sort of around every input point, and all those points in that hypercube should be assigned the same label. So let's see this very simple sort of hypercube geometric object. How does this sort of model change when it goes through the neural network? When it goes through the linear layers of the neural network, there's just a rotation, right? There's just a sort of rotation of this sort of hypercube. But when it goes through a non-linear sort of layer, then it becomes quite non-convex. And it basically has these really long protrusions that come out of it, right? So at the end of the day, like if there might be a point which is very, very close to this input point X here somewhere, but it might get deformed and might basically sort of move really, really far away, right? After these operators have been applied. Then what happens? Then there is a decision boundary that acts on this sort of hidden, like on the final sort of logic sort of layer, and it says all the points which are on this side of the decision boundary should be labeled one class, and all the points which are on the other side of the decision boundary should be assigned the other class. Now you can see why basically this is problematic. Normally, when we just train a neural network with a simple sort of loss, you just look at what side of the decision boundary is my original point. So if the black point is on the right side of the decision boundary, it's basically here, then you're like, okay, there is no contribution to the loss, so therefore I'm just going to incur zero loss, and so I don't need to change the decision boundary, even though there are now these sort of regions here which needed to be given the same label but are now on the other side of the decision boundary. And this is essentially the problem. Now, these adversarial examples essentially are on this side of the decision boundary, are represented by the pink region, which are on the other side of the decision boundary. Now, one could sort of say, well, one simple way to try to resolve this question is to just add some noise, right? Why are you working with just these point samples? You can just sample a lot of different things in your the point, and these will sort of propagate over. And of course, this sort of helps, data augmentation sort of helps, but your boundary will now basically move slightly, right? So it goes from here to here because there is now that is incurred by this contract. Does not completely solve the problem. The reason why it's difficult to cover the whole, this is a very, very high dimensional space. You cannot cover it completely, even with with exponentially number of samples. So if you generated millions of sort of points, even then you will not be able to sort of cover it completely. There will always be some sort of regions of pink space which will be on the other side of the decision boundary which you don't, which you have never sort of sampled. So then there was this idea called adversarial training, in which what people said, we will do systematic search for which instances I need to add. So what people did is basically they started from some point and then said, let me try to increase the loss. Let me try to see is there any sort of path, any way I can go on the other side of the decision boundary? So you are systematically trying to create an adversarial example, and this is what you do here. You sort of start from this black point, and then you move to the red point, and then by propagating that sort of red point back to X, you say, here's an example where this model does not work. Let me add it to the training set and repeat. And this process is very effective. And this adversarial training sort of gets you slightly better results. But it's still not able to cover all possible sort of tentacles of this very complex sort of object that has been induced by the neural network. And that's essentially the basic problem. So adversarial training is somewhat sort of effective, but it has these two limitations. It's computationally expensive. You have to sort of do the search every time, and then it's imperfect. So let me talk about the first sort of problem, that it is computationally expensive. So what can we do? The issue is that you have to work with a very strong adversary. You actually have to do a lot of work in finding these examples which are on the other side of the decision boundary. And if you don't do that, if you go train with a weak adversary, you see that the model is basically is not really robust. It creates this phenomena called gradient obfuscation, where it's very badly behaved. So gradient descent for searching for an adversary would get stuck, but that does not mean that the model is not very well. The model is very well behaved. While training with a strong adversary gets you a very good sort of well behaved predictive surface in which you don't get stuck in any sort of local optima. So the adversary can go to the global optima and can find the adversary example that if it exists, but in this case, the adversary example does not exist because you have found all the adversary examples and have added them. So in order to sort of leverage this fact that you need sort of strong adversaries which are really computationally expensive to the manifold, and somehow by adding this to the objective, you get much smoother predictive surfaces which do not behave that badly and are much more robust. I can show you the numbers. They produce very good numbers in terms of their accuracy under attack. But this is still an imperfect model, right? You have not proved that your model is completely correct. In order for you to to say that it is completely correct, you have to somehow guarantee that there is no part of this pink region that intersects with the decision boundary, right? And how would you do that? So one way to do that is if you can somehow create an outer envelope of this sort of crazy object, and if you can say that this outer envelope does not intersect with the decision boundary, then you can sort of prove that, well, now I'm totally sure that my model is perfectly robust. It does not have adversarial examples for this particular case because the outer envelope does not intersect. And this is the key sort of realization that a lot of people in the community have had, and then a lot of work has been done in basically making tighter relaxations around this sort of pink region. What we showed is that, and in fact, it was shown by sort of other people as well, that you can use a very simple relaxation. Even if you use a very simple relaxation, you don't need a very sophisticated and tight sort of relaxation. If you take a very loose relaxation, in this case just an axis-aligned sort of boxes, you just do interval bound propagation, but then you try to use that, try to basically put the looseness in the objective of the training, somehow the model sort of changes itself so that the relaxation becomes tight. So somehow you can work with a weak relaxation, but the neural network itself adapts itself so that the relaxation becomes tight. And this was a very sort of effective sort of approach for generating examples which are verifiably correct. And it basically led to the state-of-the-art results in terms of verified, robust models for image classification and for other sort of tasks. Now we have, of course, extended this to machine translation as well as to image captioning. So here we are looking at a different specification which is called conformity to output size specs. So you want to say that given a model M and a sample input X, I want to make sure that the model terminates in K steps for all inputs X prime where X prime is equal to X plus delta, X plus minus delta. Now, this is a sort of challenging thing because you are sort of thinking about these discrete sort of steps of outputs that are generated in these sequence-to-sequence models. And in fact, these models are like widely used, like in production. In all the sort of companies use these models for translation systems, for captioning, and so on. So I already sort of showed you certain sort of adversarial examples corresponding to these models. You can sort of for the machine translation models, you can sort of make them produce very sort of unstructured and long outputs. In the case of image captioning, you can sort of just change the images slightly, which force the model to hallucinate new characters. So here you see there's only 6 and 1, but somehow the neural network now hallucinates another one. In this case, it hallucinates another. It it hallucinates a 1 and 3 instead of a 7. And here it basically hallucinates 3353 instead of just 3. Right? And we were able to use the verification machinery to even sort of prove consistency for these kinds of systems. And you can also do this for other kinds of tasks. So these are adversarial examples in natural language processing. So what happens is that you might have a sentiment classifier or a classifier which is sort of detecting whether something is spam or not. And you could you might want it to be invariant to certain kind of transformations like synonym transformations or like small typos. And you can use the same sort of techniques to make the model conform with these specifications. So the same sort of machinery can be used for these applications and produce much better results. So this was the robust AI part of the talk. Can somebody tell me how much time do I have left?
So we're running 10 minutes behind, and you have until 11:45, so you have 18 minutes.
Okay, so I'm not going to take like a lot of time, but I wanted to sort of talk about this question of explainable sort of artificial intelligence. So when we think about explainable artificial intelligence, there are three sort of things, right? One is basically explaining the implementation. So you have trained a machine learning system or artificial intelligence systems, and one sort of framing of explainable AI is how is the model making its decisions. Right, so you have, say, AlphaGo playing Go, or a self-driving car controller sort of driving a car, and then you're trying to understand how exactly is it doing it. And then that is basically about explaining the task. What is the machine learning model doing? Or why is it making these decisions? So the machine learning model was sort of trained with certain sort of rewards, or it had access to certain sort of experience, whether in the form of a static data set or the experience it generated by interacting with the world. But at the end of the day, it was able to distill all that experience, whether from play or whether from sort of a data set, into its policy. And the question could be, what is the model trying to do, and why is it making these decisions? So one way that we can sort of think about this first question of how is how is the machine learning model making its decision? So one thing that we did was to distill the neural network policy into programs. So this is sort of joint work with Abhinav Verma and Swarath and other people, where we sort of train a neural network sort of policy and then try to distill that policy into a program. So now you have this, you had this large neural network, and somehow using sort of using program synthesis techniques, you were able to generate it into a compact sort of controller, which is not just compact; it is more robust. So if I show you this video, you will see here's the reinforcement learning policy driving this car, and you can sort of notice here, like it is extremely sort of volatile, right? It's basically doing a lot of different actions, while the program synthesis based controller is working extremely smoothly. And not only is it smooth, when you now take the same policies and run them on some other tracks, so in this case a new track, you see that the reinforcement learning policy would work and then it will crash. While the program synthesis based policy, which was distilled from that neural network policy, is much more robust. So one question would be, why is it robust? It was trying to imitate this other reinforcement learning policy, but it ended up being more robust. So part of the reason is that there is more stronger inductive biases in the design of the language in itself. And the neural networks have very soft or soft inductive biases, or very small inductive biases, while programs, they have a very strong inductive biases. And in some sense, those strong inductive biases give this distilled policy better generalization. So another way to do this is to basically say, let's not learn a neural network at all, let's just write a program. And this is a lot of what is done in program synthesis. You are given a very few input output examples, you are given a domain specific language, and using that sort of input output examples and domain specific language, you are able to small number of input output examples would never work in the machine learning case, right? Because machine learning models do not have that amount of that strong inductive bias. But the DSL gave you that inductive bias, which you were able to leverage to sort of synthesize appropriate sort of program for this particular task. But can machine learning help in this case? And so the challenge in sort of program synthesis is to generate sort of programs which are syntactically correct and are also semantically correct. Now, of course, you can sort of resolve a syntactically correct problem by just saying I'm going to start with a grammar and I'm just going to do grammar expansion, so everything that I sort of generate is syntactically correct. But then how do you actually sort of synthesize the program? So previous work required sort of utilized a lot of interesting techniques and structure of the grammar itself, and using sort of version space algebra was able to search over the space of possible programs that are consistent with the input-output examples and synthesize a program. If you don't want to do that, like if the DSL does not have that structure, or you want your agent to be able to sort of synthesize all kinds of programs in various different sort of DSLs, here's sort of another approach you could take. You can just take a neural network which sort of takes in your input-output examples, and then it learns how to expand the grammar to generate a program for those input-output examples. And now this sort of grammar expansion based program synthesis agent can be trained on millions and billions of possible programs. And we showed that, in fact, this can get you very, very good sort of results and allow you to sort of generate programs which are significantly, are quite sort of long. The final sort of thing, the final section of my talk is going to be sort of focused on specifications of a different kind. Now, we had looked at specifications which came in the form of reward functions, where we trained the self-driving car policy to navigate around a track. We looked at specifications which came in the form of a partial specification or incomplete specification in the form of very small input-output examples. But like think about basically AGI or basically a very intelligent agent, you can think of also having sort of tasks being specified in an informal language. And then the agent being able to sort of hallucinate and make the sort of tasks more crisp. So can you sort of have a system which can learn to sort of complete tasks which are even sort of specified by natural language? So here is one agent that we developed. This agent lives in a 3D world. It lives in like a 3D Minecraft-like world. And what the agent then needs to do is basically it is given certain instructions, and it has to then take actions in this environment to fulfill those instructions. So the instruction could be like pick up sheep. So it goes on in the 3D environment, finds where the sheep is and so forth, and then sort of picks up sheep. And it exhibits various forms of generalization, which I'll sort of talk to you about. Right. So at training time, you see certain kinds of tasks that are specified to this agent, and at testing time, you give it much longer sequences of tasks, and you give it sort of tasks which it has never seen. For example, it might have seen all the verbs and all the nouns in the instructions, but it might not have seen all the combinations of those verbs and nouns. So it might know what picking up a horse means, or it might know what sort of visiting a pig means, but it has never sort of encountered the instruction pick up pig, and we expect it to generalize to these kinds of things. So this agent has this interesting architecture, much like our brain and muscle memory, where in muscle memory you sort of learn to do certain tasks, and then the brain is sort of the reasoning engine, which is sort of telling the muscles to actually perform certain things. So we have this meta controller architecture, which is sort of telling the muscle memory or the parameterized skill part of the agent what it needs to do to be able to do. So let me show you the agent working in action. I hope this basically video is playing. So you can see here is basically a view. I'll just pause the video to show you what's happening. So on your left hand side, you see the first person view that the agent observes in the 3D environment. Right, so this left-hand side view is what the agent sort of sees. That's what it has to work with. For our purposes, just to see what the agent is doing. The agent's position is and orientation is this dot and this arrow, and this other objects are by the 2D map. Right? But this is not seen. It's basically given a sequence, and it has to do its own sort of. It has to do the transform action. It then has to go and search for the second cat. It has to then sort of perform the transform action, and it also needs to know how many cats it has transformed, and only when it has transformed 3, sort of move sort of ahead. So I'll let the sort of video play now, and you see that the agent basically is sort of transforming. It's trying to find these cats, and now it says Okay, so it has found the cat, it transforms it into some other object. Now it goes and sees the third cat, and once it has done that, then it moves its instruction pointer to visit horse. Now it basically goes and visits horse, then it goes to visit sheep and so on. Now, once it has trained, now at test time, we will expect it to generalize to much larger sequences of tasks. Right, so it is now able to do a much longer task, and not only this, it's able to sort of generalize to tasks that it has not seen. So it has seen all the verbs and all the nouns, but it has not seen all combinations, and it is able to also exhibit generalization on that. Okay, so this particular agent was trained at training time using rewards, right? So the agent would get a reward from the environment when it had successfully completed a particular sequence of tasks. But in many cases, we don't have an environment where you sort of can train the agent in this sort of way. And it's very difficult to even sort of say what constitutes success. For example, you tell your robot, I want to fold my towel in a fancy way, and you don't even know how to fold the towel in a fancy way. You have just seen it in a hotel, and you just show it certain images saying this is what folding a towel in a fancy way looks like, and this is the end state that I desire. Just change the world so that you get me to this particular state, right? And that's what we will sort of try to aim to solve in this part. So here we just give the agent certain examples of final sort of end state. So you have different sort of shapes. You can say there are shapes like diagonal line, diagonal connect, sort of line, triangles, snake, circle, square. And then you tell the agent, you start with some random state and then you tell the agent, create a triangle. And the agent has to then go and sort of navigate in the environment, pick up the blocks in that environment, and then lay them out in a particular sort of configuration which will conform to the instruction that you have sort of mentioned. And here you also have to, you can sort of have the instruction be sort of compositional. You can say make a diagonal line and it should be green, right? So then the agent has to somehow figure out that how can it create the diagonal green line here. It could create a diagonal green line here, but in this particular case, it decided that it will sort of make it in this way, right? That's for the agent to decide. We just told it get the environment into a state such that there is a diagonal line and it's green. So this is the agent sort of working. So the instructions are listed here. You now you sort of tell it make all the green blocks connected. Here you say here's a triangle, make it blue, create a blue triangle. Here you say make all the red dots connected. And so on. Here you basically say create a red line and so on. And it's basically going and sort of taking all the boxes, picking them up and sort of trying to create that sort of configuration. Okay, so I'll conclude now. And I mean, the key sort of issue here is that if you want to go after robust and explainable artificial intelligence, it's not just a technical sort of question, social question, because like machine learning has come out of statistics where the models are evaluated on the basis of data sets and benchmarks and so on. And now when we sort of try to deploy them in the real world, we need to sort of also have this notion of what are the properties and specifications they need to be consistent with. And this sort of requires a sort of a multidisciplinary approach to not only sort of formalize what are the appropriate specifications, and only then will the machine learning community be able to sort of build sort of new techniques to be able to integrate those sort of specifications. And in fact, there's a lot to be learned here from software analysis, where this sort of, in some sense, has happened over the last sort of few decades. And of course, there are technical challenges, which are how do you scale all the work that has happened on dynamic analysis and static analysis in the programming languages community, and how do you scale it to very, very large and complex neural network models, which might have billions of parameters and so on. And final sort of question is in around like in 10 years time, like how like we can all sort of agree that machine learning systems will be there and will be deployed in many different sort of applications. The question is, what will debuggers look like? Right? We know how to debug sort of different types of programs, but how do you debug a machine learning model? And those are the sort of questions that I think the communities need to think about in a more joined up sort of fashion. And with that, I'll basically open up for questions.
All right, let's thank our speaker. And we have time for a couple quick questions if you would come up to the podium. I realize that's a higher bar. All right, well, I'll start things off with one question. So I have a question about how reproducible ML relates to the kind of adversarial attacks that you mentioned. So in the example of classifying a bus as an ostrich in the beginning, if we retrained the model from the same original data set, would the result be likely to fall to the same attack from the adversary, the very same attack?
So some people have have discussed this issue, and there are certain types of adversarial examples which can be systematically created, which can transfer from one model to the other, right? So adversarial examples are both a property, in some sense, a property of the experience as well as of the model. And like the training protocol as well as the the data, and you can sort of create adversarial examples by systematically sort of targeting a whole ensemble of models, and you sort of have examples which can generalize across sort of models. But in that particular case, I'm not sure. I didn't do that sort of particular analysis. That if you retrain the model, was that sort of adversarial example robust enough to transfer? But there have been sort of examples where people have shown that particular examples can transfer.
Thank you. And we've got our second question from Ben Zorn.
Hi, Pushmeet. This is Ben Zorn. Yeah, great talk. Very, very interesting. I had a question about how you, for the adversarial attacks, how you define the hypersphere around the sample. I mean, the question I had was, you can vary the inputs, et cetera, but if you want to think about it semantically, then the thing that might be semantically very similar, like the bus, for example, to a bus, but wouldn't necessarily be close in the hyperparameter space to the original image. How do you address that?
Yeah, so that's a very, very good question. And let me go back to that sort of slide. And so in some sense, like all this was sort of a case study, right? So here, let's sort of talk about this specification. And I'm just saying that the samples need to be close by in some LP norm. But you are right, for example, for example, you might want invariance through skin tone. Now, skin tone is not sort of an LP norm, right? You can sort of say that, and cars, right? The color of the car changes does not mean that its label should change. So you can define these specifications with respect to certain attributes of X rather than the X itself. Right, and then the question is basically what would the epsilon for those features how would you compute them? And that's what I was talking about in the context of specification design. So here I was just saying let's sort of make sure that if there is another sort of example which is close in the L infinity norm, then it should be sort of classified correctly. But you don't have to sort of have specifications which are only defined on the basis of distances in in the original sort of space, you can sort of define them in feature space, where features conform to where these features represent these semantic sort of attributes, like color of skin, for in the case of face classification, or of color of hair, or whether you wear glasses or not, or like how much facial hair do you have, and so on. In the case of sort of cars, it could be different sort of shapes of cars, different sort of sizes of cars, like how far they are from you, whether the headlight is on or not, or what is the illumination condition, and so on. So you can define these semantic sort of transformations of the image, and then say that the predictor has to be invariant to those semantic transformations rather than these sort of very low-level transformations. Because we are sort of building techniques to be robust, so it's sort of a necessary condition for the future image classifiers to be robust, rather than a sufficient condition. For sufficiency, you would need to have these more richer specifications. But very good question.